my current thing was I'm planning on, actually, I think what it's going to change is I'm planning on doing, like, I've run an agent who is, all they know is their current, what's in their hand, and then I'm seeing how well that agent can do. I have a random agent, so I built those two agents so far. And then you want to build some, like, obviously then the next easy one is to construct the agent who does know the entire history of the game. But then after that, you would see if you could get like some form of recurrent LSTM network to behave almost as well as one with all the information. Because it's computationally less expensive and more interesting.
Yeah. See if it retains all the information just in the short term.
Mm-hmm.
That'd be really interesting.
Yeah. The original game was significantly more complex, but
Modeling sounds like fun, but I'm not gonna lie.
the modeling issue was already painful enough, and I was just hitting it, and like I was having to like deal with all sorts of weird tricks to try to make it, because like at one point I was considering basically having recurrent output instead of just recurrent input to deal with the fact that the action space was changing.
Oh no,
And I was like,
that
this
works.
is getting really.
Yeah, I was like trying to respond, and then one
This is almost
not
like
even long answer.
I'm looking at this and like probably write a dissertation on this one. Okay, what's a simpler one that actually shows the same concept?
And it's like, so you're typing like.
Nice.
And then I actually switched out paper because I couldn't find any one that's
wow,
done reinforcement as of it.
Might get some published.
Oh, I think it's
Well, no, it just means that I could, like, I did like the class enough to have I did a project that was like,
Yeah. That's true, that's great.
and then it might be also interesting to see if I can find a Nash. Yeah, because I don't know what the Nash fish is.
I have pencil. So something good. Environment. Oh.
All right, everybody, let's get started. So today we're going to start our discussion of exploration, and actually your last homework, homework 5, will actually be on exploration. So the material that you'll need for the homework we'll cover probably today or maybe tomorrow, depending on how far we get. So first, a few class notes. As many of you probably noticed, this semester has been a little more chaotic than usual because of the power outages. So we had to mix up the schedule a little bit. Last week we ended up skipping the lecture on meta learning because Monday there was no class because there was no electricity. We will actually still have that lecture, but we'll have it after the exploration material because we want to get the exploration material to you before your homework. So this week we'll cover exploration in 2 parts, and then next week we will come back to multitask learning and finish up the discussion of meta learning. So we'll have this little intermission for exploration, but we'll be back to multitask and transfer material afterwards. So hopefully you'll all be able to recall what we covered from the week before last on multitask when it comes time to learn about meta learning. We'll end up actually skipping one of the lectures this semester, which is the lecture on applications and advanced imitation learning algorithms, but I will post a link to a previous year's lecture on Piazza probably within the next couple of weeks if you do want to cover that material. And then homework 4 is due on Wednesday, so we gave everybody a 48-hour extension on that because of the power outage again. And this is the due date that should be on the assignment, and it was updated on Piazza. So basically everything got shifted back by 2 days. Any questions about course logistics? Okay. All right, today's lecture. So today we're going to talk about exploration. And we'll start by talking about what exploration is, why is it a problem, and why do we need 2 lectures to talk about it. We'll talk about something called multi-arm bandits and kind of more theoretically grounded methods for exploration, and what a bandit is and why it has multiple arms. We'll talk about exploration based on optimism. We'll talk about exploration based on something called posterior matching, and we'll talk about information theoretic methods for exploration. So we'll cover 3 categories of exploration algorithms, and for each one you'll see sort of theoretically principled methods for multi-arm bandits, and then theoretically less principled methods that are inspired by these for the kind of real deep RL problems that we want to tackle. So the goals for today will be to understand what is exploration, understand how theoretically grounded exploration methods can be derived, at least at a high level, and then see how we can do exploration for deep RL in practice. And this third one is probably going to be towards the end of today's lecture, and then we'll finish it up in more detail on Wednesday. All right, so what's the problem? The problem looks a little bit like the one that I presented 2 weeks ago. If you remember, at the time I showed this little animation. This is the game Breakout. Those of you that are kind of a little more enterprising might have attempted to run your Q-learning implementation on Breakout in addition to Pong for homework 3. Maybe you did, maybe you didn't, but if you did try it, you might have found that it's not too difficult. It actually tends to work decently well. If you were very crafty and looked up some other Atari games that you can run your Q-learning implementation on, you might have tried it on this one, on a game called Montezuma's Revenge, which I mentioned before when I talked about transfer learning and multitask learning. This one is quite easy. This one is basically impossible. And we could say, well, why is that the case? When we talked about transfer learning, we discussed how, to us, a lot of the kind of semantic symbols in this game have a lot of meaning. Like, for example, we understand that you can climb ladders and that skulls have sort of a negative connotation, but our algorithms don't necessarily understand that. So in Montezuma's Revenge, which is this game, you get a reward for picking up the key. You get a reward for opening the door. If you get killed by the skull, you don't actually get any reward. It's not good or bad. You lose a life, but you don't really know that losing a life is a bad thing. It just, you see this little counter decrease up at the top. And if all the counters run out, then you lose the game. But until that happens, you actually get no reward signal. So without understanding that skulls are bad, you might think this is actually a pretty positive event. For example, it makes the key respawn, so you might want to go and pick up the key again. So killing yourself is actually a decent strategy if you like getting the key. And finishing the game kind of only weakly correlates with the rewarding events. So you could do a bunch of stuff that is rewarding, but not actually contributing towards traversing the maze all the way to the bottom of the pyramid. So for us, this game is not too bad because we know what all these little pictures mean, and it's pretty easy from kind of looking at this thing to guess that the key is something that you really ought to pick up, even if you don't yet know what it does, because we kind of know from our prior beliefs about video games that picking up keys is generally a positive event, and skulls are generally not positive. To the computer, it doesn't look that way. To the computer, these are just different states, and until it gets enough reward, it can't actually figure out which of these different states are better or worse. In fact, if it has seen some number of rewarding events already, it doesn't even have a way of knowing whether this is all the rewarding stuff that can happen or whether there's other stuff available to it also. So if it picked up the key and got a positive reward, it might very reasonably conclude that the only useful thing to do in this environment is to repeatedly pick up the key, and the best thing that it can do if it has already picked up the key is get killed over and over again so that the key reappears. That's not an unreasonable conclusion based on what you know from those events. There's another game that maybe more readily illustrates this point. How many of you have heard of the card game Mao? Raise your hand. Ooh, that's actually more than in any previous year. So it looks like it's about 30–40% of the class. So it's a very frustrating card game, at least it's frustrating for me, but I think it nicely illustrates what your RL algorithm has to go through when it's performing exploration in one of these games. So Mao is one of these games where the whole point is to not know the rules. If you've heard of Calvin Ball, it's kind of a similar principle. So at the beginning, someone tells you the only rule that you may be told is this one, and then you start playing the game, and if you break one of the rules, you incur a penalty. You don't know what rule you broke, you're just told you broke a rule. And you only discover the rules through trial and error. That's essentially what an RL algorithm has to go through. It's not told anything about the semantics of the problem, it just tries stuff, and then that stuff either pays off or it doesn't. And the rules don't always make sense. And that's part of the game. So temporally extended tasks like Montezuma's Revenge, or the card game Mao, become increasingly difficult based on a number of factors, based on how temporally extended the task is. So how many things you have to do that are not themselves individually rewarding, but that lead to a rewarding event down the line, how little you know about the rules in advance, and so on. And imagine that you have a much more extreme scenario. Imagine that your goal is not to beat Montezuma's Revenge or to win a game of Mao. It's that you're kind of going about your daily life, but if you win 50 games of Mao, then you get a big reward. Now, you have no idea that this is what you're actually supposed to do. You just have to discover it through random trial and error. And since doing this even once is kind of a random and ad hoc event, unless you spend a really, really long time exploring or you do something a little bit smarter, you're very unlikely to just randomly stumble on this desirable outcome. So this is in essence why exploration is difficult, because while to us, when we approach a video game or even a card game, we bring with us a lot of prior knowledge, a lot of understanding about the world. The same is not really true for our reinforcement learning algorithms. They have to discover all this stuff essentially randomly. All right, here's another example. So these were kind of intentionally made to be kind of temporally extended games, but you can also imagine that exploration becomes a problem even when things are not temporally extended, but they are very high dimensional and continuous. So this is a robotic hand that has to learn how to pick up objects and move them to particular locations. This task presents a major exploration challenge for a slightly different reason. Even though the tasks are not actually very temporally extended, they require coordinating a very large number of degrees of freedom. So randomly moving the actuators or moving the muscles will not produce behaviors that are even remotely coordinated, which means that if you want to discover behaviors like this through random wiggling of the joints, it'll take you, again, an extremely, extremely long time. So it's not just about temporal extent, it's also about the degree of coordination that's needed and the size of the space that you're supposed to be exploring. Okay, so there are a couple of ways to nail down kind of a more precise statement about what the exploration problem really is. And I'll give you two here, but they're really kind of the same. So the first one is, how can an agent discover high reward strategies that acquire a temporally extended sequence of complex behaviors that individually are not rewarding? So this is essentially what we saw in Montezuma's Revenge. If you want to win the game, which is a very, very positive thing, you need to carry out a sequence of behaviors that by themselves are not necessarily going to provide you with meaningful reward signals. You know, some of those behaviors do, some don't, but the rewards don't really provide this trail of breadcrumbs towards the goal. A second, but very, very similar, in a sense, definition is, how can an agent decide whether to attempt new behaviors to discover ones with high reward, or continue to do the best thing it knows to do so far? And while this may at first seem very, very different, in fact, it's very similar to the first definition. If you think back to the Montezuma's Revenge example, picking up that key is a pretty rewarding thing. So an agent that is not really doing a good job of discovering that temporally extended chain of behaviors might simply choose to exploit the one rewarding thing that is found so far, which is to pick up the key, at the expense of trying out any other things, which might lead it to figure out that temporally extended sequence. So the second point is typically referred to as exploration-exploitation trade-off, which is often cast in very kind of short horizon kind of settings, but it in fact is the same thing as that top one. So it's actually the same problem. Exploitation refers to doing what you know will yield the highest reward, basically the best thing you found so far, and exploration refers to doing things you haven't done before in the hopes of getting an even higher reward. And typically those things that you haven't done before are in some ways more complicated, more risky than what you've attempted so far, because chances are, if you're exploring randomly, you'll figure out the easy and obvious stuff pretty quickly, whereas the temporally extended stuff will take a lot longer. All right, a few examples of this just to make this a little more concrete. These are kind of the classic exploration-exploitation trade-off examples. They may seem very temporally not extended, but they can be made into temporally extended scenarios as well. So let's say that you're trying to figure out where to go for lunch. Exploitation would mean that you go to the place that you like best. Exploration refers to trying something new, which may be bad most of the time, but occasionally you'll find something a little bit better. Online ad placement, something that has a great deal of monetary value. So you could show the most successful advertisement that you found so far for this type of user, or you could try showing a different advertisement. Most likely that different advertisement will not be well suited for that user, but occasionally you'll find something quite a bit better. Oil exploration. So you could drill at the best known location for oil, or you could try somewhere else. Now, hopefully you have a little bit more information than just simply picking a random point on the globe to use for oil exploration, but in general, again, the exploration strategy will in most cases yield a worse result, but occasionally find something much better. Now, exploration is a very difficult problem. In a very formal sense, it's a difficult problem. But we could ask this question: can we derive an optimal exploration strategy? Now, if we want to pose this question, we have to actually nail down a very precise definition for what it means to be optimal or suboptimal. So one of the things we can talk about is the amount of regret that your exploration strategy incurs when compared to a Bayes optimal strategy. What is a Bayes optimal strategy? Well, a Bayes optimal strategy is something that actually calculates your belief about what the rewarding events are, and then takes the optimal action that will lead to the highest reward in expectation over all possible beliefs. So if you think that opening the door has some chance of being of leading to a good outcome, then you can kind of hedge your bets by opening the door some percentage of the time. And we'll come back to this later to make this more precise. Now, in general, we can study exploration for problems of varying complexity, and they'll fall somewhere on the spectrum between theoretically tractable problems and theoretically intractable problems, with most of the problems that we actually care about being on this end of the spectrum. And what will determine where these problems fall in that spectrum is basically the degree of temporal dependence in those problems. So the easiest problems will be things like multi-arm bandits. You can think of multi-arm bandits as essentially stateless RL problems, so RL problems that have one time step and no state. So you essentially just take one action, you receive a reward, the episode ends, and then you get to take another action. A slightly more complex version of this is what's called contextual bandits, which are single time step RL problems that do have a state. So in a contextual bandit, you receive a state, which is referred to as a context, and then you're asked to make a decision. So a contextual bandit might be, for example, the ad placement scenario from before. A user comes to your website, you observe their feature vector, which might be, for example, the websites they visited in the past. Then you make a decision, which is which ad to show them. They click on the ad or don't click on the ad, and then you get the next time step. There is some analysis that can be done on contextual bandit problems. Slightly more complex are small finite MDPs. So these are MDPs where exact planning, exact solving is tractable with things like value iteration, where you know all the transition probabilities and so on. But they do have temporal extent. And here, oftentimes, you can do very nice analysis of optimal exploration by framing the problem as one of identifying the model in the MDP. And then on the far extreme of theoretically intractable are large or infinite MDPs, things with continuous state space and so on, which are actually most of the problems that we deal with in this class. So the way that we're going to approach exploration then is we'll first discuss these simpler, more tractable problems, and then devise algorithms for tackling the larger, more complex problems that are inspired by those more tractable solutions. All right, so what makes an exploration problem tractable? Well, so here are kind of the easy ones. For multi-arm bandits and also for contextual bandits, you can actually formalize exploration as a partially observed Markov decision process. It's almost like a meta-level partially observed Markov decision process. So even though the actual episodes in these bandits are one-time step long, you can view the entire exploration process as a very long MDP, where you have partial knowledge about what the underlying rewards are, and you can actually reason about the best actions to take to sort of identify those rewards and achieve the largest reward overall. And that will actually give us a way to solve for the Bayes optimal solution for bandits. And it turns out that because they're so simple, actually learning that policy is fairly straightforward. For small finite MDPs, you can still analyze them a little bit. We won't talk about it in this lecture, but you can frame the problem of solving these MDPs, of exploring in those MDPs as a Bayesian model identification problem. And then you can reason explicitly about value of information and figure out what the best exploration strategy is. We will discuss a little bit some stuff regarding value of information, but we won't go through this in too much detail. And then in larger infinite MDPs, the kind of optimal methods from before don't really work because the problem is just way too large. But you can take inspiration from those methods and design more heuristic techniques that still achieve good results in practice, but don't have the same kind of theoretical grounding. So that's basically the high-level sketch of how our discussion of exploration will go. Does anybody have any questions? Yes?
So to what extent can Montezuma's revenge be solved by reward engineering?
So the question was, well, to what extent can Montezuma's revenge be solved by reward engineering? Any RL problem can be solved very, very well with reward engineering. One trivial example of a reward that will solve your RL problem is to take the optimal policy, give your agent a reward of +1 million to take the action that matches the optimal policy, and -1 million for every other action, and then you can solve the problem trivially. The question is, do you have the knowledge that is required to do that? But modifying the reward function can always solve any RL problem if you have perfect knowledge of the optimal policy. Any other questions? Okay. Oh, and this will look like using hacks. So this is kind of continuing the theme in deep RL. The way that we actually end up solving most problems is to use hacks. But hacks that are inspired by the good principled solutions. All right, so let's talk a little bit about bandits. So what's a bandit anyway? We talk a lot about bandits when we discuss exploration, and we're not talking about this guy. We're actually talking about a kind of model problem that represents, in a sense, the Drosophila of exploration problems, the simplest exploration problem that allows us to get at the underlying issues and to analyze this and understand it in detail. So the term bandit comes from a popular American colloquialism for a slot machine. And the reason that it has multiple arms is that we're not talking about just one slot machine, we're talking about a whole lot of them. So in a single slot machine, you have one action, which is to pull the arm. I guess if you're a little more creative, you have actually a second action, which is not play the game, but we don't give you that option. You have to pull the arm. So a single slot machine is not very interesting, but if you have a whole lot of slot machines, then you might figure out that pulling the arm for some of them is a lot better than others. So maybe that second slot machine is the one that likes to give you a lot of money, and you'd rather pull that arm than any of the others. And that's basically the game. So each arm has a different reward. So AN refers to pulling the nth arm. You don't know what the reward is a priori, but you might have some initial belief about the reward for each of the arms, and then by trying different slot machines, you might discover which one is more or less rewarding. And of course, they're slot machines, so the actual payoff you get from each of them is random, but those random rewards have different distributions for different slot machines. So you might assume, for example, that your reward is distributing according to some distribution conditional on your action, and there is a true distribution for the world, which you don't know in advance, but you might have some prior, and then you might update your beliefs as you pull the arms and learn more and more. All right, so before we get into the details, we're going to all play a game. We're going to actually play a game where we will pull different arms, but these won't be actually slot machines. It'll be something with slightly higher stakes. It'll be a medical diagnosis problem. So let's do that. Let's do a little bit of medical diagnosis. I assume none of you here are actually qualified to do this. None of you have a medical degree, so we will be about as uninformed as, oh, I don't want 40. Let's do 10. We'll be about as uninformed as the RL algorithm. Okay, so here's the game. We've got patients that come to us, and they have some disease. And we have 4 possible drugs we can prescribe. And if you prescribe the right drug, then the patient will be saved. And if you prescribe the wrong drug, well, you get the picture. So we're going to vote. And let's see, how can we do this? Well, how about you guys raise your hand, and you can raise like 1 finger or 2 fingers or 3 fingers. And then I'll do my best to gauge what the popular sentiment in the room is. So patient number 1 comes in. Which drug do we prescribe? Okay, cool. So number 1 seems to be the more popular one. Okay, well, that didn't go so well. You've got 9 more chances before they revoke your medical license. Patient 2? All right, that was very, very clear consensus. Let's go with drug 2. Not so good. Patient 3? Okay. Some of you were voting 2 again, but most of you voted 3. Okay, something happened. That person lived. Patient 4. This is the interesting one. Okay, all right, all right. Looks like 3 is the winner again. Okay, patient 5?
Oh, what happened before?
He lived. It's good. You guys saved him. Okay, patient 5 looks like 3 is the winner. Okay, patient 6? All right. Uh-oh. Patient 7? Okay, now I have to actually look through this. Okay, looks like the 4s have it. Uh-oh. Patient 8? Okay, back to 3. Patient 9? Still 3, okay. And last one? Okay, 3. All right. So here is how you did. So this is showing the true drug efficacy. So drug number 3 was in fact the most effective one. You guys just got pretty unlucky a couple times. And 2 and 4 were by far the worst. And what this is showing is, well, the number of lives saved. So the purple one, the worst one there, that's you guys. So you can say goodbye to your medical license. And then the other plots here show different methods, many of which we will actually cover in today's lecture. So the cyan one, this one called UCB, that's the next one we're going to talk about. That one did quite a bit better than you guys. We'll talk about posterior sampling, the yellow one. And, well, and the epsilon greedy, that one you guys already know. And the greedy one is the one that just always plays the best drug, which was pretty close to what you guys actually did, except for that one time when everyone decided to vote for. So, okay, I might complain that you guys did badly, but actually I think the truth is that you guys got a little bit unlucky. So that's good news for homework 5 when you'll have to actually do this for real. All right, so, all right, this we already saw. The patient did not live very much. How can we define the bandit? So for the bandit, we're going to assume that the reward for any action is distributed with some probability that depends on that action. So for the drug prescription problem you saw before, the rewards were always 0 or 1, and the parameters of that distribution was basically a number between 0 and 1, which you saw in that plot there. So drug 3 had a probability of about 0.9, 2 and 4 had a probability of 0.1. So there are a number of different ways you can parameterize this. It depends on the semantics of your problem. So if you know your reward is binary, maybe there's just a number theta I associated with each action. If your reward is continuous, maybe it's the mean and variance of a Gaussian. Your parameters are assumed to have some prior, which you know. Your prior in the drug prescription case was just a flat prior over all the numbers between 0 and 1. But otherwise, you don't really know anything else about the parameters other than their prior. Now, one of the things that's kind of interesting about this is that this is actually enough for us to define a partially observed Markov decision problem. It's not the same MDP as the actual bandit problem. It's sort of a meta-level MDP. In this meta-level MDP, the state is actually the parameter vector that generates these rewards. So the state can be formed by concatenating all the probabilities of all the rewards. And it's partially observed because you don't actually know what those parameters are, but you have a belief over those parameters, and you observe evidence that allows you to infer them, namely the rewards. So your belief is your estimate of the probabilities of these theta 1 through theta n. So this is kind of what you guys were probably doing in your heads when you were playing the drug prescription game. You were thinking, well, what's my current guess as to the likelihood of each of those drugs actually curing the patient? And you probably guessed pretty quickly that 1 and 2 were fairly low numbers, and 3 was probably a pretty high number, which is why even when you saw drug 3 kill the patient once, you thought, well, maybe I should still do drug 3 because it's probably a pretty high number. Now, the cool thing about viewing this as a PUMDP in this way is you can actually solve that PUMDP, and you can obtain the optimal exploration strategy. Solving a PUMDP is pretty difficult, but this is not a very large PUMDP, and it is actually possible to solve it with some kind of approximation, but still a pretty good approximation. Now, in reality, that's actually overkill. The belief state is still pretty large, and even though you can get a fairly accurate solution for a small number of arms, there are much easier ways to get an equally good solution. So if you really want sort of the gold standard, you can solve the PUMDP, but we're going to talk about a number of strategies that asymptotically are just as good as solving the whole PUMDP. So you can do very well with much simpler strategies, many of which we'll cover shortly. Now, when we say do very well, of course, we need some measure of goodness. We need to know what it means to have a good exploration algorithm. And the measure of goodness that we use is something called regret. So when you prescribe the wrong drug too many times, too many patients die, you have a great deal of regret about that. And that's the regret that you'd like to minimize. So the regret is formally defined as the difference from the optimal policy at time step t. So if you've prescribed 8 drugs, you've played that game 8 times, now you're going to have a regret at time step 8, which is going to be the difference between what you got and what the optimal strategy would have gotten, the doctor that actually went to medical school and knew which drugs to prescribe. So formally, we can define it like this. The expectation of R of A star, that is what the optimal policy would have gotten. So the doctor that went to medical school knows which drug to prescribe, that's A star. They might still not cure the patient every time, so this expected value of R of A star might not be 1.0, it might be like 0.9 or something, but that's the best you could possibly do with perfect knowledge. And then it's multiplied by capital T, which is how many episodes you've played. And then this is what you got. So you take what the expert would have gotten, subtract what you got, and that's your regret. So the smaller that regret is, the better our exploration algorithm is doing. And that's what we'd like to minimize. Yes?
Why do we need this objective instead of like the normal RL objective, which is to maximize your reward? Because it seems to be identical.
Yeah. So the question is, why do we want why do we want this objective instead of a normal RL objective? So this bit is a constant. So no matter what strategy you play, this doesn't change. So you can also view this as being negative reward plus a constant. The reason that we analyze regret is because with regret, we can actually say that the regret for better algorithms is lower, and we can actually say that it scales with some function. Like you say, okay, the regret goes as log of t. If you have a regret that's log of t, that's a very good regret. So it is just a constant and a negation for the standard expected reward, but it turns out to be much more convenient to deal with these quantities for the purpose of analysis. Yes?
We're minimizing regret. Why don't we just, like that assumes we already know the optimal policy, so why don't we just act the optimal policy?
Yeah, so the question is, if we're minimizing regret, don't we need to know the optimal policy to calculate this? Yeah, so in reality, you would use regret as part of your analysis to try to understand whether your exploration algorithm is good, but then once you have that algorithm, you would use it in settings where you do not know the optimal policy. Of course, if you don't know the optimal policy, technically you can't actually quantify your regret. So for unknown problems, we can't actually quantify this number, but we can use it to analyze and compare different exploration methods. Okay. All right. So how can we actually do a good job of minimizing this regret in some exploration problems, let's say for now in the bandit setting? Well, there are a variety of relatively simple strategies that actually can work very well. Many of them can work provably well, and some others can work very well in practice. Typically, the way that the analysis of these kind of strategies go is that you want to show a bound on regret in expectation. And there are a variety of algorithms that are all actually equally optimal up to a constant factor. But empirically, their performance can vary a little bit depending on the parameters of your problem. Exploration strategies for more complex MDP domains, like the deep RL settings that we study in this course, are actually going to be inspired by these strategies, but will lack the same theoretical guarantees, because providing those guarantees for high-dimensional or even continuous problems is extremely difficult, and we don't actually know how to do that right now. So let's start with the first strategy that we'll learn about, and that's actually one of the simplest, but also one of the most effective. So let's say that you're playing the game, and maybe I'll tell you that the rewards are continuous, so they're not like these 0-1 rewards you had in the drug prescription problem. They're just real valued numbers, anywhere between negative infinity and positive infinity. One of the things that you might do is you might keep track of the average reward that you've seen for each action. That's a pretty reasonable thing. And then if you want to figure out the best action, well, you could just pick the one with the largest average, right? That's a pretty sensible thing. So this is essentially exploitation, doing the best thing you've seen so far. Pick the action A, that is the argmax of your estimated mean, mu hat A. Now, what might be the problem with this? Why might we not want to do this every time? Any suggestions? Yeah.
Because it won't explore very well, so we might find, like on our first try, something that has a very stable but very bad average that's slightly above our 0. We'll just keep grabbing that and miss the giant high reward off one action.
Yeah, so that's basically the answer, that this thing won't actually explore very much, which means that it might stumble onto some moderately rewarding action pretty early on and not bother trying anything else, even if there might be other actions that are much, much better. So can we explicitly change this objective in the argmax to prevent that? Can we essentially artificially improve the perceived goodness of things that we haven't done yet? Any thoughts about how this could be done? Yeah?
Maybe add some bonus for things you haven't tried very often?
Yeah, so let's try to add some bonus for things you haven't tried very often. A very straightforward one might just be everything that you've never tried, everything that has a 0 visitation so far, you just have to try that. Like if you've never tried it, let's just go and do it. But more generally, you can have some optimistic estimate. So you can say that instead of picking the argmax of mu hat A, let's pick the argmax of mu hat A plus some constant C, which determines how much you prioritize exploration, times some value sigma A, which is some quantification of your uncertainty about A. So intuitively, sigma A should be something that is very big for actions that you've rarely tried and very small for actions you've tried a huge number of times. And there are a lot of choices to be made in the design of sigma A. So you could just say maybe sigma A is infinity for things you've never tried because you don't know anything about them, and maybe some small number for things you have tried. So it's some kind of variance estimate, some kind of estimate of uncertainty. So the intuition behind this strategy is that you're going to try each arm until you're sure that it's not great. So if you think that something might be good, just try it a few more times just to make sure. But once you're confident that it's not good, move on to something else. And it turns out that very simple choices for sigma A actually tend to work very well, both in theory and in practice. So one very simple example is this particular UCB-like rule, which says that your bonus is going to scale as the inverse square root of the number of times you've tried that action. So if you tried an action 0 times, then that number is basically infinity. If you tried the action 1,000,000 times, it's 1 over the square root of 1,000,000. And then in the numerator, you have 2 times the natural log of t. Intuitively, what that does is it says that as you've tried something many, many times, or as you've tried the whole thing many times, this numerator will grow a little bit, and you need a large denominator. OK, so that's the number of times you've picked this action, and the numerator is the log of the number of episodes. It turns out that if you use a rule like this, or actually many other rules that have some kind of denominator that grows with n, you get a regret that is O of log t, which is actually provably as good as any exploration algorithm for bandits. So if someone tells you, my exploration algorithm has a O of log t regret, that means that they're actually doing as well as they possibly can. Obviously up to a constant. Now, of course, in practice for complicated deep RL problems, there are many other ways to estimate these uncertainty estimates, and we'll talk about quite a few of them. But if you have a bandit with countably many arms, then this kind of strategy, which is called the UCB strategy, tends to work quite well, and in fact is provably the best you can do, although in practice some other strategies might work out a little bit better in terms of the constant. All right. Let's talk about another exploration strategy. This one takes a little bit more inspiration from the kind of PumDP view of this. You can think of this as a very model-free style exploration method. This one is going to look a little more model-based in nature. So this is called probability matching or posterior sampling. So remember that from the PumDP view of exploration, you can keep track of a belief over the parameters of your PumDP. Those parameters basically determine the rewards for each of the arms. So this is, in a sense, a model of your bandit. If you know theta, then you know how your bandit works. You don't know theta exactly, but you have a belief over it. So you can view it as a distribution over bandits. You don't know what the current bandit actually is, but this p hat gives you a distribution based on the evidence you've seen so far. So here's an idea. What if you sample a parameter vector from your belief? So say, let's pick a bandit according to the distribution that I believe for the current bandit. And let's act optimally with respect to that model. So perhaps we think that the parameter value for one arm has a very large distribution. So there, if we pick multiple samples, we'll get very different rewards. The parameter value for some other arm has a very narrow distribution. So there, no matter how many samples we pick, we'll always get the same outcomes. So let's sample an entire bandit model from this, pretend that this model is correct, and then take the optimal action. It turns out that if you do this, you also get a very effective exploration algorithm. Of course, in practice, it's going to look a little bit like that UCB rule, because if you have some arm that's very uncertain, you'll sometimes draw parameter vectors that assign it a very high reward, and sometimes not. And then, of course, after you take that optimal action, you're going to update your belief. And then repeat. So this is called posterior sampling, sometimes also referred to as Thompson sampling. It's substantially harder to analyze theoretically, but it can work very well empirically. And in fact, many very effective exploration algorithms for larger MDP problems will be based on this idea. If you want to learn a little bit more about the theory behind this and some of the analysis, you can read this paper by Chappell and Lee called An Empirical Evaluation of Thompson Sampling. I won't go into the analysis too much, but we'll see this idea come up again when we talk about deep RL exploration. Any questions about UCB or posterior sampling? Yeah?
Is T fixed before a problem?
Is T fixed before a problem? So T meaning the T in regret, this thing that I said is log of T?
Yeah.
So this is just the number of time steps that has elapsed so far. So you say, OK, like I'm at type step 17, T equals 17. So this thing actually changes. OK. The third and final kind of more principled exploration method that we'll talk about is based on information gain. And here I'll need to do a little bit of setup before I introduce an actual exploration method, because I need to describe how Bayesian experiment design works. So here's the idea. Let's say that you want to determine the value of some random variable z. So you don't know what z is, but you have some probability over z. Z might be, the optimal action, or maybe the value of the optimal action. So what do you do if you want to figure out the value of z? Well, let's say that h of p hat of z is the entropy of your current estimate of z. So you don't know what z is, but you have a probability, you have your current belief p hat of z. So that's the probability that you currently assign to different values of z based on what you know so far. And that belief has a certain entropy, meaning that if you have a very precise belief, you know exactly what the value of z is, its entropy is very low. If you have a very imprecise belief, its entropy will be very high. And let h of p hat of z given y be the entropy of your z estimate after some observation y. So someone told you y is equal to this, that changes your belief about z, and then maybe you have a lower entropy over p hat of z. So now you can immediately think about how the difference between these two quantities in a sense captures how much you've learned about z from observing y. So if y is like literally the value of z, then observing y tells you everything. If y is completely unrelated to z, then observing y tells you nothing. And things that are in between will tell you a little bit of information. So y might be, for example, the reward you get from taking some action. So it's some bit of evidence that you would get. So now the lower the entropy, the more precisely you know z. So you can define a quantity called information gain, which is a function of z and y. And information gain is the expected decrease in entropy over z. So to compute information gain, you don't actually observe y. You haven't yet taken that action. You don't know what y is going to be, but you have some idea of what y might be based on your belief. So you say, if I take this action, I think I might see this, but I might also see that. And integrating out that y, you can calculate the expected change in entropy. So it's essentially a statement about how your beliefs will change based on what you currently believe about what the evidence will be. And typically, of course, you don't just want information gain z comma y. You want information gain z comma y conditional on some action, right? Because you actually want to take some action in the world. So then you'd say, if I take action A, based on what I know about my system, I might observe this value of y with probability 0.1 and this other value with probability 0.9. So let's average them together and calculate my expected information gain. So it's a quantity that can be calculated using only your current beliefs. And then when you actually take action A, then the uncertainty resolves itself. You actually see some y. And then you can update your belief over z. So now you might think that, well, if you want to identify z as accurately as possible using the smallest number of actions, maybe the best thing for you to do is to take the action that has the largest information gain. So let's work through an example of how this could actually be used for exploration. So the information gain tells you how much you learn about z from action A, given your current beliefs. Here's an example of a paper that uses this idea for exploration in bandits called Learning to Optimize via Information-Directed Sampling by Russo and Van Roy. And they choose y to be the reward of some action. So their evidence that they observe is the reward. That's pretty straightforward. That's basically the evidence that you get when you play with a bandit. The z, the thing that they want to learn about, is theta A, meaning the parameter of the true reward model. That makes sense. You want to learn what the true reward model is. The evidence is the actual rewards that you observe. And the actions are the actions, the arms of the bandit. And they set up their exploration rule as following. So they define this quantity, g of A, which is the information gain about theta A from Ra, given the action A. And they define this other quantity called delta A, which is the expected suboptimality of A. So based on your current belief about the bandit, it's the expected value of the difference between the reward of the optimal action and the reward of a particular action A. So intuitively, you'd like to take actions where delta A is pretty small and where g of A is pretty large. And what they analyze is an exploration rule like this. You take actions according to the argmin of delta A squared divided by G of A. So that means that actions with a small G of A are ones that you'll very rarely take, so don't bother taking actions if you won't learn anything. But also don't take actions that you're sure are very suboptimal. So if delta A is very, very large, then you also won't take that A. And then they study this and show that it also achieves the optimal regret. Now there are, of course, many other information gain-based techniques you can devise, basically corresponding to different choices for Y and for Z. But this is the one analyzed in this paper that seems to work decently well. And then we'll see some deep RL methods that are also based on this idea. OK, any questions about information gain? All right. So a few general themes from this discussion. There are basically three exploration rules that we've discussed. UCB, which essentially takes your expected value of your reward and then adds some kind of novelty bonus to it to prioritize pulling arms that you haven't pulled very much. Thompson sampling, which maintains a belief over the parameters of your bandit, and then samples from that belief, and then acts optimally with respect to that sample. And information gain, which tries to quantify how much you learn about aspects of your bandit from taking different actions, and then prioritizes actions from which you'll learn a little bit more. Now, most exploration strategies require some kind of uncertainty estimation, even if it's pretty naive. So, this one has a very sophisticated uncertainty estimation involving maintaining beliefs over these different quantities, whereas the UCB rule has a very simple kind of uncertainty estimation that just says things that you haven't done very much are more uncertain. But there has to be some kind of reasoning about novelty or uncertainty. Usually you assume that there's some value to new information. That's a very reasonable assumption. So you might assume that unknown things are good, which is optimism, which is essentially what you have here. You might assume that your sample corresponds to the true model, which is what you do in Thompson sampling. Or you might assume that acquiring new information is an inherently good thing, which is what you do in information gain. All right, so why should we care about these kind of bandit problems, even though they're not really the problems that we're going to be mostly concerned with solving? Well, they're much easier to analyze and understand, which means that we can get some theoretical guidance on the design of these exploration methods. We can derive foundations for our techniques, and then we can apply those ideas to more complex MDPs. Sometimes the application of those ideas to more complex MDPs will be largely heuristic in nature, but we'll have at least some reason to believe that these things might work well. Now, there are a bunch of things that are related to this that I didn't get a chance to cover in this lecture, like, for example, contextual bandits, which are bandits that have state rather than just having arms. You can also study optimal exploration in small multi-time step MDPs, so long as they're tabular, meaning that they admit an exact solution. And you can also do Bayesian model-based reinforcement learning, very closely related to information gain, where you actually reason about the entire model of the MDP. So I'm not going to get a chance to cover those, because I do want to get to the exploration methods in deep RL. All right, so at this point, I'm going to take a short break. We'll come back at 11:01, and then we'll talk about exploration in deep RL. So see you all in 3 minutes. Yes?
About the information gain side,
Mm-hmm.
can you get
Yeah, sure.
back to yeah, here. So in delta, there is optimal strategy involved,
Mm-hmm.
right? Do we know it a priori? Like how
So this is the belief about the optimal strategy.
oh, so we do like expectation.
Yeah, so the expectation is taken under the agent's belief about the model.
I see.
So it's basically saying, if you think some action is really, really bad, don't do it.
Yeah, makes sense. Okay.
Yes, I have a follow-up question. So would it matter how good your initial beliefs are about the system?
Yeah, absolutely. So your initial beliefs are derived from your prior. If you have a very, very good prior, then you might basically solve the bandit right away. If you have a really ridiculous prior, it might take you a really long time.
Okay.
You might even have an informed prior that is wrong, in which case it would take even longer than if you knew nothing at all.
Right. So is the prior learned separately ahead of time, or is it like?
So
as part of
yeah,
the
so
exploration?
typically in these settings, the prior is assumed to be given.
I see. Okay. All right. Thanks.
So you said you can calculate information gain, but isn't information gain taken as like an expectation? So like, what do you need to know the true state in order to calculate the expectation?
So the expectation here is taken with respect to your beliefs. The only thing that's unknown are the parameters of the bandit, so the parameters of those P of R distributions. So you just have to integrate over all the...
Calculating like an expected information?
Yes.
So like, if your model is drastically off, is there any guarantees on convergence?
So yes, there are guarantees on convergence, but it will take longer if your prior is wildly off.
Any way to like quantify that to ask
I don't know. I'm sure people have looked into this. I just don't know off the top of my head.
I actually run into weird issues of it, finding a local optima. I'm doing something similar to this in my project. I find a local optima and then it gets stuck there. Is this something that would mitigate that?
A little hard to say without knowing more about what you're doing, but in general, yeah, like you can think of local optimal problems in RL as essentially being exploration issues. So if you remember the discussion about exploration versus exploitation from before, you know, the agent in Montezuma's Revenge deciding to always pick up the key is a kind of local optimal problem because it has to do something highly suboptimal before it finds a better solution. So you can sort of view that as a little trough in the energy landscape. So yeah, in that sense, better exploration methods could potentially address the issue.
Okay.
All right, let's continue. So before the break, we talked about these kind of more principled exploration methods. Now we're going to talk about exploration in deep RL. And as with many things in deep RL, it's going to be less principled, but substantially more applicable. So we talked about optimistic exploration, which basically says that a new state that you've never seen before is a good thing, so you should seek out new states. And this requires estimating state visitation frequencies or novelty. And typically this is going to be realized by means of exploration bonuses, so we'll cover that shortly. We'll talk about exploration methods based on ideas like Thompson sampling and posterior sampling, but of course now that we don't have a bandit problem anymore, we have a full MDP, we have to learn distributions over something more applicable to our MDP, like Q functions or policies, instead of the parameters of the reward. And then we'll sample and act according to that sample. So we might maintain a distribution over Q functions. For every episode, sample a Q function from that distribution, act according to that, and that will realize a Thompson sampling strategy. And then we'll talk about some information gain style algorithms, which reason about the information that you'll gain from visiting new states. And the question there will be information about what, and we'll see a few choices there, like for example, information about the dynamics of the MDP. All right, let's start with optimistic exploration first. So in the world of bandits, we saw this exploration rule. You take the argmax of mu hat A plus some bonus that gets bigger as n of A gets smaller. So that's our exploration bonus. Now there are lots of functions that will work for this exploration bonus. The important thing is they have to decrease with n of A. So as n of A gets bigger, the exploration bonus gets smaller, meaning that rarely visited things have a big bonus, frequently visited things have a small bonus. So can we use this idea with MDPs? Well, yeah, we can. It's just that in MDPs we have states in addition to actions. So our bonus now is a function of states or a function of states and actions. For most of the more general analysis, we'll use bonuses that depend on states and actions. But it's pretty easy to imagine that if you have a small number of actions but a huge number of states, maybe the actions aren't really what matters, and it's enough to have a bonus that only depends on state. For many practical problems, bonuses that depend only on state are perfectly adequate, but for the most general analysis, we should have them depend on states and actions. And then what we'll do is we'll incorporate that bonus into our reward. So you can think of the UCB rule for bandits as choosing the action with the largest reward. In RL, it's a little more complex because you have temporal dependencies. So you might want to choose an action now that has very low reward so you can get high reward later. So in order to allow our MDP solver to reason about that, we'll actually add the bonus directly to our reward function and then use our favorite reinforcement learning algorithm on top of that reward function, which means that our reinforcement learning method will actually take care of those temporal dependencies for us. It'll figure out that some states that are reachable downstream that have very low frequency are ones that we should endeavor to reach, even if in order to get there we have to go through many frequently visited states. So we'll take our old reward function and we'll add some function of our count of our n of s, and that function is b. And intuitively, b just needs to decrease with n of a, or n of s. And then we'll just use this r plus of sa instead of r with any model-free algorithm that we want. So that's the basic architecture for optimistic exploration in RL. But of course, there's a little bit of a catch there. We have to actually maintain track of these n of s's, and they actually have to mean something in our problem. Does anybody see any problems with this? Imagine using this to play Montezuma's Revenge. Yeah.
Maybe you don't visit the exact same state twice.
Yeah, maybe you don't visit the same exact state twice. So maybe maintaining these n of s's is a little bit problematic. So what's a count? So here's a picture of Montezuma's Revenge. Maybe I'm going to count how many times this guy has been in this location. But this guy isn't the only thing that matters. The skull matters too. So maybe what I'm going to do is I'm going to count how many times that guy has been in that location while the skull was in the same exact place. But of course, the skull and the guy can occupy many different places. So if there are like n locations for each one, now I have n squared possible combinations. But the key also matters, so I have to keep track of that. So if the key can be in n possible states, and I have n cubed possible things. And the more things there are in the state, the more different things I have to count, the less likely I am to ever actually see the same state twice. And in general, if all the pixels in this image can change, maybe I will actually almost never see the same exact pixel accurate image 2 times in a row, which means all my counts will be either 1 or 0. That's very bad news. Things can be even worse, though. You could, for example, have a continuous domain like this. Now, if my state consists of the pose of this robotic hand, now I'll definitely not see the same thing twice, because even though they're fixed precision floating point numbers, the chance of having all the bits be exactly the same is negligible, so all my counts will again be 0 or 1, which means that this method is not really going to do anything useful. Intuitively, I somehow need my counts to generalize a little bit. I need them to figure out that a state that I've never seen before that looks very, very similar to another state somehow has lower novelty than one that looks totally different. So I need some notion of similarity between my states in order for this to work. All right, so some states are more similar than others, and we need some machinery to take care of this. Now, fortunately, we do have some machinery that understands similarities between states, and those are our function approximators, or deep neural networks. So we're going to have to use our function approximators to help us generalize a little bit. So here's the idea. We're going to fit some kind of density model to the states, or to the states in action. So we'll fit some kind of density model that I'm going to call p theta of s. And the job of this density model is to give us a number for every state, such that that number is small for states that are very novel, and large for states that are similar to states we've seen before. This is a density modeling problem, a generative modeling problem. So p of s might be high even for a new state s if it's similar to previously seen states, if our density model is generalizing a little bit. And later on, we'll see many different choices for these density models, so don't worry about that for now. Just assume that we have some kind of density model. Before I talk about what those density models might be, I want to talk a little bit about how we actually incorporate them into an exploration rule. Because before we needed counts, we needed n of s. And now we have this p of s, which doesn't seem like the same thing. So can we somehow use p of s to get a kind of a pseudo count? Something that can be used in the same way as a count, but generalizes a little bit. So if we have a small MDP with a countable number of states, like a tabular MDP, there's a very convenient relationship between probabilities and counts. Right? The way that you estimate probabilities is you count how many times you've seen S, and then divide by the number of times you've seen all other states, or all the states including S. So the probability of S is just n of S divided by little n, where little n is the total number of states you've seen. Very, very simple rule. That's how you estimate probabilities, as we probably know from introductory statistics. So this is the probability, this is the count, and this is the total states visited. Now, after you see S, of course, your count will go up by 1, and the total number of states will go up by 1. So P prime of S, meaning the probability after you've seen S, is given by this equation. These are both true statements. So that means that if you don't have n, but you do have P of S and P prime of S and little n, you can actually solve for what n of S should be. So can we get P theta of S and P theta prime of S to obey these equations? Well, the answer is we can, because it's basically a system of equations with some known and unknown quantities, and we can solve them and figure out what n of S should be given P of S and P prime of S. So the way that we explore with pseudo-counts is you fit your model, P theta of S, to all the states seen so far. So these are basically all the states in your buffer, D. Then you take a step in the environment and observe some new state, Si. And then you fit a new model, P theta prime, to the union of all the previous states and this new state. So you essentially concatenate the new state to your buffer, refit your density model. And then you're going to use your old model and your new model to estimate n hat of S. So n hat of S is a pseudo count. It's basically your estimate of what n of S would be if you were doing real counts. And then you set your reward to be the true reward plus some function of n hat of S. So just substitute n hat of S in place of actual counts. And then you repeat. So how do you get n hat of S? Well, you use these same equations from the previous slide, and you just solve for n hat of S. You have two equations and two unknowns, so you just do a little bit of algebra, and you get a solution. If you don't want to do that algebra, I can do it for you. Here's the algebra. You can check at home, make sure I didn't make a mistake. But if you plug this in, then you'll get your n hat, little n hat, and big N hat, and then you just substitute it in there, and it acts like a better version of a count. How much better? Well, depends on how well your P theta of S generalizes. If your P theta of S generalizes very well, then you'll get really nice solutions. If your P theta of S doesn't generalize very well, then you'll be no better off than you were with normal counts. All right, so what kind of bonus should you use? Well, there are lots of functions in the literature. They're all basically inspired by optimal methods for bandits or small MDPs. And how well they actually work for deep RL problems largely ends up being an empirical question. But I'll give you a few examples. So the rule from UCB, this is the one that we saw before the break, is to take 2 times the natural log of little n divided by the big N and then take the square root of that whole thing. There's another popular rule, just do 1 over n of S and take the square root of that. That tends to work decently well too. Or you can just do 1 over n of S, that also works. The second one is the one that's actually used in the pseudo-count paper. But your mileage may vary, and since in deep RL all bets are off as far as the theory, just use whichever one works best. Does it work? Well, yeah, it actually ends up working pretty well. So the learning curves here, the black line shows regular Q learning, essentially what you implemented for homework 3. And the green line shows this 1 over square root of n exploration rule. And you can see that it does quite a bit better. This is a little visualization of Montezuma's revenge. So without any exploration bonus, you visit the first room, and you occasionally visit the second room. With an exploration bonus, you visit a whole bunch of rooms, including these really interesting ones that have like lava pits and stuff. So that's really good. You can do better than this, but this is actually a decently effective method, and it's quite simple. Now, an important choice for making these exploration bonus methods work well is to choose a suitable kind of model for P theta of S. You need the model to output densities, but it doesn't necessarily need to produce great samples. So while there are a lot of methods that you might learn about for example, if you study generative modeling or unsupervised learning that estimate models of this sort, the kind of considerations that you have for deep RL are often a little bit different than in classic generative modeling. So in classic generative modeling, we typically want to fit P of S type things because we want to sample new states. So if you train, for example, a variational autoencoder or a GAN, you don't really care whether it's producing good probabilities, but you mostly want it to produce good samples. Here the considerations are the opposite. We really want these things to produce good probabilities, and we don't really want to sample from them. And that will change the kind of models that we typically want to use. So it's opposite to the consideration for many popular generative models. The particular model used in the original pseudocount paper is something called a CTS model, which you can think of as almost like a kind of a little Bayes net over pixels. So it's actually not a deep model. It just says, let's model the probability of a pixel as being conditioned on its upper left neighborhood. And then you can use a chain rule to basically model a probability over every pixel this way. It's not a particularly great generative model. Like, it doesn't actually produce good samples, but it gives you some notion of novelty. But there are many other choices, and I'll talk about some of these next. So one of the things you could do is you can borrow some ideas from hashing to try to get a slightly simpler and maybe more effective method for computing these novelty bonuses. So what if you still count states? So you're still going to compute literally the number of times you've seen something, but in a different representation. Maybe a more compressed representation. So one idea might be to take your state S and compress it into a k-bit code via some compression function phi of S, and then count the number of times you've seen the same code. Essentially count the number of hash collisions. The shorter your code is, the more hash collisions you get. So choosing a smaller k intuitively will result in exploration that smooths out the states better. Choosing a larger k will bin the states more finely, result in fewer collisions, which means that you'll distinguish between the states better, but you might also get too many of those 0 or 1 counts. Now, will similar states get the same hash? Maybe. I mean, in principle, good hashing algorithms should actually do the opposite, but maybe you can learn your hashing function in such a way that similar states are more likely to get the same hash. So that's what was actually done in this paper by Tang et al., where the idea was to improve the odds a little bit by actually learning a compression function by training an autoencoder. So what they do is they train an autoencoder, a neural net that maps an image back to itself through some bottleneck. The bottleneck has k units, and those units are binarized to produce a k-bit hash. And then they simply count the number of times the same hash has occurred before. The shorter the hash, the more often they get hash collisions, and in effect, the more smoothed out their state similarity is. And that also works decently well. So here, there are a number of different hashing methods that are actually considered. The red one just does things at the level of pixels. The green and blue one do different variants of the autoencoder type hashing. And the orange is the baseline that just runs regular, in this case, policy gradient. So you can see that the green and blue lines tend to do quite well on a lot of these tasks, substantially better than the baseline. So something here is working. There's another model that we can try to devise, one that doesn't require actually training any kind of autoencoder or any kind of generative model at all, by observing an interesting relationship between classification and densities. So remember that P of S doesn't need to actually be good for producing samples. It just needs to output densities. It needs to output numbers that indicate the probability of a state. So can we get these probabilities by explicitly comparing a new state to past states? The intuition is that a state is novel if it's very easy to distinguish from previous states we've seen before. And by distinguish, I mean by training a classifier. If you train a classifier that distinguishes between a new state and previous states, and that classifier is very, very accurate, that means that that state is very different from states you've seen before. If it's extremely difficult to train that classifier to distinguish a new state from past states with high accuracy, that means that there are states you've seen before that are very similar to your new state. That's the intuition, but it can actually be made very precise. So let's set this up a little bit. So for each observed state S, we're going to fit a classifier to classify that state against all path states D. So that means that the positives are a set with one element, which is S, and the negatives are all the path states that you've seen. It's a somewhat peculiar classification problem, but it's a well-defined classification problem. And then it turns out that we can recover a probability on S. If D of S is our classifier, the probability is simply given by 1 minus D of S divided by D of S. Why is this true? Well, so D of S is the probability that the classifier assigns that the state S is positive. where the set of positives is just S and the set of negatives is all the states you've seen before. And let's work through the math. So first, you might think there's something very, very strange going on here, because isn't this classifier just checking if S is equal to S? Like, shouldn't that be a really, really trivial problem? Well, it turns out the answer is no, because remember that the set of negatives is a set of all states you've seen so far. If the same state also appears in the negatives, then the optimal D of S shouldn't assign a probability of 1 to S itself. It should assign a lower probability. So if I've seen state A in my negatives 5 times, and I've seen state B in my negatives 5 times, and then I'm seeing that state in my positives, now the right probability to assign is more like 0.75 or something like that rather than 1.0. In fact, you can show that the optimal classifier would assign a probability to S of 1 over 1 plus P of S. The reason for that is that the optimal classifier for any classification problem should be equal to the ratio between the probability of the positives divided by the probability of the positives plus the probability of the negatives. And you know that there's only one state in the positives, which is S itself, so that becomes a 1, and then its probability in the negatives is P of S. So from this relationship, you can do a little bit of algebra and solve for P of S in terms of that classifier. So it's a little bit of an algebra trick. Now, of course, in reality, the same exact state will not appear in D, but maybe a very similar one will, in which case, if your classifier is appropriately regularized, you might recover that relationship. In fact, the regularization actually ends up being quite important for this, so things like weight decay are usually necessary for this to work. Now, the other objection with this scheme is that, well, maybe one classifier per state is a bit much. Like, this amounts to saying, I'll just train an entire neural network classifier every time I see a new state, which is rather extravagant. So, of course, what we would do in practice is we would train one amortized model, which is a single network that outputs a classifier for any state. So it takes in an x star and an x, and it outputs dx star of x. So this input basically says which state are you trying to classify against all others, and this is the state for which you want to obtain the probability. So essentially, this amounts to amortizing the cost of training all these thousands and thousands of classifiers and stuffing it into one network, a network parameterized by which state you're trying to classify against all others. And that now makes it a lot more tractable, because now you have one network instead of a million networks. And again, this tends to work decently well. It tends to work especially well on kind of image-based tasks, because for images, it's quite difficult to build good density models, but it's pretty straightforward to train classifiers on images using ConvNets. Any questions about any of the methods so far? OK, so there is one more technique I want to talk about, and I definitely want to make sure I cover this, because this is most likely what will be on homework 5 for you. So far, we've talked about methods that somehow estimate this P of S, either by directly fitting a density model or doing that trick with the classifiers. But it turns out that we can actually get away with estimators that don't even output great densities. Like, they're not going to output great samples. They don't even really need to output great densities. They just need to output densities that tell us if a state is novel or not. So long as this number is big for previously seen states and small for states that you've rarely seen, we're actually OK with that. Like, we don't need those probabilities to be extremely well calibrated. And we can exploit this a little bit by devising a much simpler way to estimate our exploration bonuses. So let's say that you have some function, we'll call it a target function, f star of s comma a. So it's some function, some scalar valued function on states and actions. Let's say this is the function, right, this green line. And you have your buffer of states and actions. So let's say that those are the blue dots. So these are the states and actions that you've seen. What we can do is we can fit some estimate to this function, which we're going to call f hat theta. This is basically a neural net. And we're going to fit that f hat theta to try to match the function f star as closely as possible using our buffer as our training points. So maybe if I have only these 3 training points, when I fit f hat, it'll correspond to this orange line. Right, during training it only saw the blue points, so it's going to be very close to the green function on the blue points, but it might be quite far from that function, far away from the blue points. So now, if all I want is some quantity that is small close to the data and big far from the data, how can I get that quantity from knowing the green line and the orange line? Any ideas? Yeah.
Just take like a square difference between them?
Yeah, like just take the square difference between these things. So we can just use this error E, which is the squared difference between f hat and f star, as our bonus. Because if f hat theta did a good job of fitting f star, it's going to have a small difference close to our blue circles, so that'll be low novelty, and it'll have a big difference far away from our data. Now this is of course very, very simple. In fact, it's simpler than many of the techniques I've covered so far. Now we do have to choose some kind of f star. So we need some kind of non-trivial function for this green line. If f star is really, really simple, maybe f star is always 0, then maybe we'll get some, maybe the orange line will fit it a little too well, and that won't be any good. Any ideas about what we could use for f star? If I just showed you this slide and then I told you for homework 5, implement this, what would you choose for f star? Yeah.
Maybe have it be like the dynamics model or like the reward model.
Okay, so it could be the dynamics. So maybe f star of s comma a is the next state s prime. It could also be the reward model. Maybe f star of s comma a is equal to the reward. That's nice because you actually observe those things. So when you interact with the MTP, you actually know what those targets should be. And even though you don't know the true dynamics or the true reward, every time you visit a state, you know its reward. So you can actually evaluate that error. That's very, very convenient. So even though you don't know the green curve, every time you actually visit a state, you observe the value on the green curve. So that's quite feasible. Any other ideas? What else can we use for f star? Yeah.
The target Q values.
We could use target Q values. That's kind of cool. I'm not sure what that would do, but maybe it's worth a shot. So you've got those target Q values because you're learning a Q function. Maybe worth trying as an experiment. Any other ideas? All right. So let's see if my prediction last night agrees with what you guys suggested. So what should we use for f star? So one very common choice is to use the dynamics to basically set f star of s comma a to be the next state. In fact, there are quite a few methods that do this. A lot of them go under the name of curiosity. So there's a classic paper by Jürgen Schmidhuber that does this from the early 90s. This is also related to information gain, which we'll discuss on Wednesday. But it turns out that you can do something even simpler. See, the function f star of SA has to be non-trivial, but it doesn't have to be particularly intelligent. It doesn't have to actually mean anything. So you could even choose a random function. There are many ways to construct random functions, but one that's very convenient if you already have TensorFlow installed is to just set up a random neural network. So just set up a neural network with, let's say 3 layers, and randomly initialize its parameters, and use that as your f star. And that turns out to actually work quite well. It's actually simpler than using the dynamics, because you'll know this function everywhere. And this results in a method called random network distillation, which is what we're going to try to have you do for homework 5. You could also try this S prime thing if you want, but this is going to be easier. All right, so on that maybe slightly surprising note, I'm going to end today's lecture, and I'll see you all on Wednesday for a discussion of posterior sampling and information gain in DeepRL.
For you, partners are working on the project, right? And we have chosen as a representative AI problem researcher.
Okay.